I put an extra credit project here, ML100, so you can do some machine learning at the bottom of the 121 Computer Forensics page. And here it is. And the great thing about this is you do not need a virtual machine or anything. You can only use a web browser because Google provides a free environment to do this kind of work in. There's one good thing about Google. They invade your privacy and mess with you, but they give you a lot of free service like Gmail and stuff. And Google Colab is one of the great free services. You do have to sign into a Google account. I'm going to sign into one of my accounts here, like CNET121, one for this class. Okay, once you have logged into a Google account, you can now make a new notebook. They call it a Jupyter Notebook, these things. And what it is just a Python environment that you can use to write code and run it on their server. And it'll run on their server CPUs. You can even add GPUs to it to make it faster. But what we're doing here is simpler. And we're going to use this thing called TensorFlow. This is the Python code that imports the TensorFlow library and then just prints the version number. So we run it with the run button, of course, and the output will appear here. It's getting ready. And up here it'll tell you how much RAM and disk it gave you. It gives you a certain amount of RAM and a certain amount of hard disk space. And there we are. It ran it. Now it's version 2.15, which is fine. Any version is fine for what we're doing here. So here's the essence of machine learning. If you have this kind of data, you have X going up by 1 and Y is down here. And first thing that's obvious is that X goes up, Y goes up 2. Then you can notice if X goes up by 1, Y goes up by 2. And when X is 0, Y is minus 1. So the mathematical expression of this is Y is 2X minus 1. Now this is how a human does it. And what you want in machine learning, you could write a computer program with this equation in it and predict these numbers. But what we're going to do is learn this trend from the data. That's what machine learning does. You just give it data and it will figure out the relationship. So this is the code that does that. And the great thing about it is very, very easy. It only takes about 10 lines of code. So I can have another block of code here. And what's going to happen here is I import some libraries. This defines a model. And this will compile the model using stochastic gradient descent, which is the standard way you do it. It's going to use the mean squared error as a measure. And here's just the X and the Y. It's going to fit it in 500 steps and then predict the value at 10. The right answer at 10 is 19, 2x minus 1. So if you run this, you can see it go. And what's going on is it starts with random values for the parameters. It's only got one neuron, it's a slope and intercept, so it has a loss that's really high. And stochastic gradient descent, it figures out which direction will make the loss smaller, and it takes a little step in that direction. And so it makes it a little bit smaller, a little bit smaller, a little bit smaller, and takes 500 steps. So the loss that was originally 20 gets down to a really small number by the end. Down here at epoch 300, the loss is like 10 to the minus 4 because the data is perfect. The loss could in principle get all the way down to 0. You can fit a straight line perfectly through that data, but it got it down to 10 to the minus 5, which is pretty close to 0. So its prediction at 10 is 18.98, and the right answer is 19. So it's a very good model. All right. Now, here's what it looks like if you graph this thing out. It has one neuron, and the neuron has only two parameters, a slope and an intercept. And the perfect answer is a slope of 2 and an intercept of minus 1. And you can run this model, and you can print out the weights. The weights are those numbers it learns that it puts on the neuron. So I'm going to add another block of code. This is going to do the same thing again, but now it's going to print out the weights at the end. And the correct answer for the weights are 2 and minus 1. So again, it's going to do 500 little steps. See, the loss is getting really small again. And when it's done, it has 1.997 and minus 0.991. So this is close to 2 and this is close to minus 1. So it's a pretty good fit. It got within 1% of the right answer for this. So that's learning a simple activity. So now we're going to give it some errors. I'm just going to put some noise in it. So I'm going to change it. And now that you have this program, go back to it and just change the Y's. So I'm going to change it to this. Now, I could just do it that way. It might be a little bit more polite to comment out the first one. There, so now instead of 3, I have 3.1. Instead of 1, I have 0.95. I just changed the numbers a little bit. So they're a little bit noisy. So let's see how well it goes now. And now the loss can't get as small. The loss was getting down to 10 to the minus 5. But with that much noise, there probably is no way to get the loss down that small. In fact, it looks like it's kind of hit the bottom here at 0.004. Is as good as it's going to get. However, it's still got 1.99 and minus 1.00, so the trend is still fitting pretty well, but there is some noise. And here's the prediction at 19. All right, and there's a flag there. All right. And then you can try fitting a parabola. Now here's a parabola, x squared minus 4x minus 5. So that's these values. Now the thing about those values is they do not fit on a straight line at all. And yet I'm going to try to fit them with this model, which is always only going to fit a straight line. Because I only have one neuron, and it's only got a slope and intercept. There are only 2 parameters to fit. So if I do this, the loss is never going to get very small at all, because it's trying to put a straight line through a curve. So you see, its loss now never really gets below 4. So it's going to be pretty terrible. And the correct value for 10 is 55, but its prediction for that point at 10 is minus 12. So it's wildly off. And this is like that curve I showed you before, like Donald Trump used to predict that COVID was just going to fall to 0. When you have the wrong model, you get a bad prediction. So we can also fit a complex curve. This is a more interesting case. A straight line is, of course, so easy. You don't need a computer to do it. You don't need artificial intelligence to do it. So more complicated curves would be more interesting. I think I'm going to make a new notebook. I could keep running with this one, but I'd rather just get a clean one. So it's, I already had signed in. I shouldn't have to sign in again. That's rude. All right. Well, in the wisdom of Google, they're making me sign in again. All right. Then a new notebook. All right. So now I can put in this stuff. And so what this one is going to do is it's going to use, go from minus 10 to 10. It's going to make 1,000 points. And it's going to use 0.1 times cosine of x plus noise. So it's going to be a curvy curve. And it's going to have a more complicated model. Instead of just one neuron that has a slope and intercept, it's going to have one neuron at the input layer, then 64 neurons at a hidden layer to calculate, and another 64 neurons at another hidden layer to calculate, and then one output neuron. So this, I think if, let me diagram that to try to make that more clear. I'll just use a plain text editor here to get a picture of some sort. So the idea is you have x coming in. Just there. Then that's your one input. Then you have a whole bunch of neurons here. So they're all getting that X, and each one of them is doing different calculation on it. That's a whole layer of hidden neurons doing the AI, and then another whole layer of neurons, and then you have one coming out of here. So this data feeds into all these neurons. There are different weights at every point. Every one of these neurons, the output feeds into every one of these with a different weight at every point. So instead of just having 2 parameters like the straight line does, slope and intercept, this is going to have hundreds or thousands of parameters that can be adjusted. So it can fit a curvy shape, and that's what it's going to do. So with two layers of 64 hidden neurons, then you just train it and graph the output. And it's working. Been going for 5 whole seconds. There we are. So it created a model. Now here it tells the number of parameters. If you only have one neuron, there's only 2 parameters. But this, you have 2 parameters in this layer. You have 128 parameters in that layer. You have 4,000 parameters in that layer because it has each of the 64 in them. So total number of parameters is 4,355, a whole lot more than 2. So I have 4,355 adjustable parameters, and there it went through 100 epochs. And as you can see, it did a pretty good job of fitting the data. The red is the prediction, the blue is the data, so that worked pretty well. Now you can play games to see how different models work. You can use fewer layers. Let's just have only one hidden layer instead of 2 hidden layers of 64 neurons. So that's easy. I'll just comment out one of them with a pound sign. Now it's got one input neuron to take X, 64 to do the calculation, and one output neuron to do Y. That instead of having 4,000 parameters, it's going to have a lot less. It's now got 195 parameters instead of 4,000. And so the fit should be a lot worse, and well, it's worse, but I wouldn't say it's a lot worse. It's still pretty much following the trend, but anyway, that's one way to go. And so there are various versions here. You can have only 32 in there. You can have, there's one here where you compare various things, like only 4 units per layer, but 3 layers. Let's try that one. If instead of 64, I have 4, but then I'm going to have 3 of those layers. So I'll copy that line. If I can get it to go, there we go. There. Now I got 3 hidden layers with 4 neurons in each layer. And so the total number of parameters is still pretty small, only 55. So you might imagine it's going to do a pretty bad job, and well, I'd say that's a pretty bad job. Yeah, all right, anyway. So that's what you can do, get an idea what's going on here with curve fitting, which is essentially all it's doing. So that's what I wanted to show you about that one. Let me check for comments. All right, there aren't any, so I'm going to stop this recording.